Alrighty guys, welcome back. Today we're going to be talking about the ideal gas equation of state. We're going to give you some examples, we're going to show you what that is, it's that PV equals nRT formula, and we're going to show you how it's applied in engineering problems. So let's go ahead and jump in and see what we got. Looking up a density or specific volume at a temperature and pressure for a liquid or solid, and using those values at a different temperature works just fine. But the same is not the case for gases. For gases, we need a special equation that relates specific volume to temperature and pressure. This is where the equation of state comes in. The equation of state relates molar quantity and volume to temperature and pressure, that is, PV equals nRT. So keep in mind that it is only an approximation, but it is a very good one, and if used correctly, it can yield errors of less than 1%. And I'll show you how to calculate those errors as well. And this is ideal for gases at low pressures. Gases start to deviate significantly at high pressures and or low temperatures. So this is what we got. PV equals nRT. And that's for closed systems. If we have a system that has input and output with respect to time, we have PV equals nRT, but with dots on the V and a dot on the N. V dot being volumetric flow rate, N being molar flow rate, P being pressure, R being your gas constant, and T being your temperature. Now it's important to note that these are your temperature, these are your values in what we refer to as absolute. So for example, temperature would be in Kelvin, and that's just a rule of thumb. That's just how the formula is set up. So if you're given a PV equals nRT formula and you're told that it's going to behave ideally, or that the substance that you're given in the problem is going to behave ideally, you know your temperature has to be in absolute units, and that you would have to convert it to kelvins. Now, this is the description for this right here. It's also equivalent to this over here, but V would be your volume and N would be your moles. So identical, just depends on what kind of system you're given. Another thing to note is pressure has to be absolute. And I'll explain in detail in a bit what that means. This formula could also be written as so: PV hat equals RT. And the derivation for this formula is this. Let me highlight these real fast. These are the formulas you got to know, but the derivation is this. Let V hat equal V over N. If you were to rewrite this formula, PV equals nRT, and rewrite it like this, P times V over N equals RT. I just divided this over here. And we let this equal V over N, where V hat equals V over N. We could therefore write P V hat equals RT, and that is the formula we have written over here, and it is equivalent to the one we have up here. We could also say this. We could also say that V hat equals V over N, or V dot over N dot, and that is also totally valid. Now, V hat does have a special name. V hat is called your specific molar volume. Whenever a gas behaves ideally, it is also said to be a perfect gas. If the gas is in low pressures, then you're in an okay spot. If you start getting high pressures and insane amounts of temperature changes, then you might have a problem and you might have a non-ideal gas, and different equations would have to be used for those kinds of problems. But typically you're going to be told that the gas behaves ideally, and when you're told it behaves ideally, you should be thinking PV equals nRT or PV hat equals RT. Both equations are equivalent. It's just a matter of what information you're given in the problem and how you could plug it in to get your final answer. So, as I said before, using PV equals nRT will yield errors less than 1%. And that's important because you don't want to be using a formula that's going to get you large margins of error. But you got to know how to calculate those margins of error. And to do that, you use these formulas. So these are the formulas you use. And here you're told that V ideal equals RT over P. That is, V ideal equals R times temperature, R being your R constant or your gas constant, divided by pressure. And V is your V hat or V ideal, the one we defined earlier above. If either one is greater than 5 liters per mole, then it will have a percent error of less than 1% for diatomic gases. And this is only for diatomic gases. Now, if V ideal or V hat ideal equals RT over P, if either one is greater than 20 liters per divided by mole, then your percent error is going to be less than 1% for any other gas. Your diatomic gases would be nitrogen, oxygen, fluoride, hydrogen, the ones that have like that pair, that H2O2, N2, those kind of gases. If you have other gases like methane, which is like CH4, then you would need to fulfill the criteria that it has to be greater than 20 liters per mole instead of 5 liters per mole, which is for diatomic gases. So let me give you an example of how this plays out, and it'll give you a better understanding of these rules. So, example. Here we're told we have 100 grams of nitrogen, and it is stored in a container at 23 degrees Celsius and 3 psi G. PSI is pressure per square inch, something like that. G stands for gauge, and that's going to be important in a bit, and I'll explain why. First part once, assuming ideal gas behavior, calculate the container volume in liters. Number 2, verify that the ideal gas equation of state is a good approximation for the given conditions. So, let's break down what's given to us. We're told ideal gas behavior. Perfect. Because we're told it's ideal gas behavior, we got to think PV equals nRT. Whenever you come across a problem that says ideal gas, perfect gas, think PV equals nRT. Should be your number one thing you associate with ideal gas behavior. And then calculate the container volume in liters. Well, ideal gas behavior, okay, PV equals nRT. And they want us to find liters. That is volume. Perfect. V equals nRT over P. I just divided pressure on both sides and got this new formula. Now, we know what R is. That's usually just a constant we look up on a table. We can just Google that value or check our textbook. It should be available somewhere, but we'll hold off on that part for last. Temperature. Well, we're given it's 23 degrees Celsius. But remember, because we're going to use PV equals nRT, it has to be in absolute units, meaning we have to convert it to Kelvin. How do we do that? Whenever you have Celsius and you want to convert it to Kelvin, you add 273.15. When you add 273.15, you get Kelvin. But for our purpose, we'll only add 273. So 23.0 plus 273 equals 296 Kelvin. Okay? Great. So we have R, we have T. What about pressure? Do we have pressure? Pressure, we're told it's 3.00 psi G. Remember how I told you that G is gauge? And remember how I told you above the pressure has to be absolute? Well, this is the formula you got to use to make sure they're in the correct units. P absolute equals P atmospheric plus P gauge. We have this and we need this. So what is this? Well, P atmospheric is usually 1 atmosphere, 760 millimeters of mercury, or 14.7 psi A. And that's just something you're going to have to memorize. There's no hidden tricks here. It's not hidden in the problem somewhere. They're just values you have to memorize or look up in your tables if you're allowed to use them during your exams. Therefore, P abs is equivalent to 14.7 psi A plus 3.00, and that's equivalent to 17.7 psi absolute. And finally, we got to find moles. We're told we have 100 grams of nitrogen. Convert that to moles, we use the molar mass or molecular weight of nitrogen, and that is 28 grams per 1 mole. And that gives us 3.57 moles of nitrogen. And therefore we have everything we need to find our volume. So at this point we just plug stuff in and get our final answer. 3.57 moles. Your R value, which I'll hold till the last part of this problem, and then temperature 296 Kelvin. All over pressure, and that's going to be 17.7 psia. Now you're probably wondering, how do I get rid of these units? Because I have mole, Kelvin, and psia, and I want liters. Well, finally, we could look at this R. And the reason why I wanted to hold this R off was I want you to look at the units you have here, mole, K, and psia. Whenever you look up your R value, you want to look up an R value that has these units. That way, when you plug it in here or multiply it by these other K, mole, and psia, it'll cancel out. So if we use a reference chart, and it could be any chart on the internet as long as it has R values that are universally used across most problems, and it's not some sketchy website, then you should get and find this following R value. I'm going to go ahead and delete the R value from here. Just put a little dot here for meaning multiplication. And I'm going to say that this is my R value. I just moved it over. Same thing, multiplying it by these over here, nothing changes. And finally, we see that we have Kelvin, Kelvin, that goes away. And we have mole, perfect, mole and mole. Well, let's see, we want liters, so we probably don't want to get rid of that. But we have atmospheres and psia. So we use our table and we look for a unit conversion factor, one that relates atmospheric and psi. And we find this. We find that 1 atmospheric is equivalent to 14.7 psi. Perfect. We could cancel this, we could cancel that, we could cancel atmospheric, and we could cancel atmospheric. And that leaves us with liter. Perfect. That's what we needed. That's what the problem wanted us to find. Now keep in mind, this psi here, your textbook or your chart might say it's psi. It's also equivalent to psi absolute. Whenever they give you values for psi, they're typically psi absolute unless otherwise specified. But it's always good to double check what your book is giving you. PSI gauge, PSI atmospheric, or PSI absolute. Now, if we simplify this into our calculator, we get the following value. 72.0 liters. And that's our final answer. This is V ideal 72.0 liters. Okay? It's V ideal because we used PV equals nRT, and we started using a whole bunch of middle people, like converting it from Celsius to Kelvin, converting PSIG to PSI absolute. We use those relationship factors to get 72.0 liters, and that volume is V ideal. Finally, we want to confirm that the formula we use, PV equals nRT, is a good approximation for this problem. We don't want to just start plugging numbers in and get a result that it's nonsensical or going to give us a huge error in our system. So let's go ahead and verify that. Remember the formulas I give you? The ones that give you a yield error of less than 1%? These formulas right here? We're going to use these formulas. Remember, V hat ideal equals RT over P, and we do have RT over P, therefore we have V hat ideal. So let's go ahead and plug in values and see what we got. If V hat equals V over N, then V ideal equals V ideal over N. That is V hat ideal. And because we know what V ideal is, that is over here, we could simply write this. 72.0 liters divided by moles, and our moles is 3.57 mole as we calculated above, and our final answer is 20.2 liters per mole. And what do you know? Nitrogen is a diatomic gas, right? So we want to look at this rule right here. And 20.2 is definitely greater than 5 liters per mole. And therefore, we say that we have a percent error of less than 1%. So, because it's greater than 5 liters per mole, our error is less than 1%. And that's a very good thing. Pro tip, we can also use the RT over P values for the same answer. .2 liters per mole. So to summarize, whenever we have a gas and we take measurements at a specific temperature and we want to use those measurements at a different temperature, we got to be using the PV equals nRT formula, because that method of just taking stuff at one temperature and using it at another is only good for liquids and solids. You're going to get really big deviations if you start using it for gases. That's where PV equals nRT comes in, and it allows you to make very good approximations with very low errors. And you can verify these errors by following these formulas here and determine if the route you took is a good one to solve the problem. Again, ideal gas behavior associated with PV equals nRT. If you have any questions, leave them in the comment section below. This is your Chem E tutor, and I'm signing off. Take care.